equal to 1, but all these your connected loads are on, then maximum demand will be equal to total connected load. In that case, it will be 1. Otherwise, it will be always less than 1. Right? It is true for everything, not only your residence, as a whole also. Right? When you talk about power system, industrial consumer, agricultural consumer, like this. Right? So then utilization factor. So it is the ratio of the your maximum demand of a system to the rated capacity of the system, right? Thus the utilization factor is maximum demand of the system, rated system capacity. For example, suppose in a power plant you have a few generating units, 100 megawatt, say 125 megawatt, 200 megawatt rating. You add all this, right? And at a particular time you see what is the maximum demand of the system, right, in 24 hours. And so maximum demand by rated capacity, so it is expected, it is also, it will be less than equal to 1. Later in numerical we'll see that this value also, it's called, it's your what you call this, less than equal to 1. And this is utilization factor. Basically it depends, it is this utilization factor is used for the generating plant, right? So then plant factor, so it is also known as the capacity factor or use factor. It is the ratio of the total actual energy produced over a specified period of time to the to the energy that would have been produced if the plant had operated continuously at maximum rating. Idea is very simple. You look at this definition. Plant factor is the actual energy produced by maximum plant rating into time. For example, suppose in a plant, maximum plant rating altogether, say you have 4-5 units, say total is 800 megawatt. Suppose if you see that in a year you want to find out what is plant factor, then T should be 8760 hours, right? And in annually, what actual energy is produced, it will be less than that your denominator part, right? So your plant factor will be always less than 1, right? So it is the maximum plant rating into the time. If time is year, then 8760 hours, and then over the years, what is the actual energy produced? This meter is there, they measure actually how much energy is produced, right? So that is actually plant factor. If plant factor is high, means this is the maximum use of the your what you call the generating units, right? So it is also true for the generating plant, right? And an annual plant factor is given actually. Sometimes we call annual factor the actual energy generation by maximum plant rating. Here one thing is there, that it is actually, it is not actual, it will be annual energy generation, right? This is a correction, so you please correct it. This is actually annual energy generation, right? And this is one T is missing in this equation, is maximum plant rating into T, right? Here it is your here it is actually in that equation, it is actually not actual, it is actually annual energy generation, right? Annual energy generation divided by maximum rating, and T is missing in the typographical error, it should be T, this T is missing, right? So it is actually annual energy generation. So here it is on correction. Wherever it is there, I'll tell you. So annual plant factor will be, it is actual annual energy generation or actual energy generation. I am writing actual energy generation divided by maximum plant rating, in if annual is 8760 hours, right? So this is called plant factor. These are very simple actually. This first chapter is very simple. Then diversity factor. So diversity factor is that it is the ratio of the sum of individual maximum demand divided by coincident maximum demand. Suppose in a plant, suppose in a load, you have industrial load, agricultural load, commercial load, residential load. So every load has its individual maximum demand that will not happen together, right? And that's why you sum up individual maximum demand divided by coincident maximum demand. I mean, it is something like this. It is something like this. Suppose you have, suppose this is your time, and this is your load demand, right? This side, I mean, I'm just plotting it. Sometimes we plot it like staircase. So for example, this is one consumer is there, one consumer is there. This is, for example, say in the industrial consumers. Another consumers may be there, say agricultural consumers, maybe like this, right? Another may be commercial, say commercial, maybe it will be here, it will be going like this, right? So in this case, individual maximum demand means this is individual maximum demand, say for industrial consumers. Say for commercial, this is industrial residential maximum. Therefore, residential, this is individual maximum demand, right? And when you your what you call add every hour, you add all these three generation, you will get a single plot. Maybe it will be going like this, right? And this is your coincident maximum demand. I mean, all the hours you are what you call, you are adding and see that which is the maximum, right? So that's why the meaning is that your sum of individual maximum demand by coincidence maximum demand. In general, diversity factor, demand factor, we have defined DF. That's why diversity factor I have taken as FD. So FD is equal to I is equal to 1 to n sigma Pi upon Pc. Or Pi is maximum demand of load I. Load I means it may be commercial, it may be industrial, it may be residential, it may be agricultural. That is the load I divided by Pc. Pc is the coincident maximum group of n loads. I just told you graphically, right? That means every hour you add all these loads and see where the peak is going, right? So, or another thing is the diversity factor is maximum demand by total connected load, right? So can be equal or greater, this value can be equal or greater than unity, because when you are adding sum of individual maximum demand and this is the coincident maximum demand, this sum will be greater than PC. So your diversity factor will be always greater than 1, right? Extreme cases it will be equal to 1, but it will not happen. It is always greater than 1. So diversity factor also can be defined as maximum demand by total connected load, right? So this is diversity factor equal from equation 1.1. The demand factor is, I mean, from equation 1.1, if you come, the demand factor is maximum demand is equal to demand factor into total connected load, right? Therefore, demand factor is equal to maximum demand by total connected load. That is from equation 1.1. Therefore, maximum demand is total connected load into demand factor, right? Now, for the ith consumer, suppose if the ith consumer means that it may be industrial, agricultural like this, right? If ith consumer, let us assume the total connected load is equal to TCPI and the demand factor is DFI. Therefore, equation 1.8, this equation can be written as that your PI is equal to TCPI into DFI, right? Therefore, from equation your what you call 7, that is 1.7, and your 1.9, so demand factor is that FD is equal to can be written as, because PI here, PI is equal to your TCPI into DFI, so you substitute here. So demand factor will be FD is equal to sigma I is equal to 1 to n TCPI into DFI upon PC, right? This way you define. Therefore, this is very simple actually, just little bit of practice. Coincident factor. So it is actually reciprocal of your diversity factor. It is actually CF is equal to coincident maximum demand by sum of individual maximum demand. It is just your reciprocal of this one, equation 1.6. It is just reciprocal of equation 1.6, right? So this way you define coincidence factor, that is CF is equal to PC upon sigma I is equal to 1 to NPI. So this is your coincident factor, right? Therefore, coincident factor is reciprocal of the diversity factor. CF is equal to 1 upon FD, right? So these are very simple. Now load diversity. Load diversity means that your difference between the sum of peaks of two or more individual loads and your what you call and the peak of the combined load. That means suppose it is actually sum of individual maximum demand minus that coincident maximum demand, right? I mean, suppose agriculture, industrial, everything. Suppose agricultural load is 80 megawatt, industrial load is 200 megawatt, for example. So 280 will be, and say coincident megawatt is just say PC will be 240 say. So it will be 280 minus 240 is equal to 40 megawatt. That means sum of individual maximum demand, right? Minus your what you call coincidence maximum demand, right? This is actually load diversity. How much diversifier?
So,
Tell me.
so FD is diversity factor and DF is demand factor, right?
Demand factor. I have defined, because if I make both D, like when I was writing this out of book, I think this is diversity factor. I have taken FD, right? I didn't use DF because there will be confusion then because of
So both are
demand factor.
different, right?
Different. Of course, different. Right.
Okay, sir.
Yeah. Okay. Different. So that's why I have not. So no confusion. DF is demand factor and FD is the diversity factor. Right. Then contribution factor. These are the certain terms they use during the planning, particularly at the generating plant, and particularly and sometimes and other thing is at the downstream, that is at the distribution level, right? So suppose that contribution factor. Contribution factor means it is given in per unit of the individual maximum demand of the ith load. Actually, per unit system we will study in this course. I am not sure. Electrical machines you have studied, no? Synchronous generator, induction machine, everything you have studied or not? You have already studied in your fourth semester or fifth semester?
Yes, sir.
There you have studied anything on per unit system, per unit reactance, per unit power, per unit voltage? Studied or not? Just to tell me.
Sir, not in detail, but in short.
Yes. But here you will in power system later you will study in detail. I one complete chapter is there on a power unit system, and everything will be represented by your dimensionless quantity. Then you will find that calculation will be easier. After that, you convert it to original this thing. When I will cover per unit system, at that time you have to understand very carefully, because your electrical engineering. But just hold on. Somebody wants to join. I think. Just hold on. Just hold on. So later I'll teach per unit system. Before moving anything, after inductance, capacitance, all these things I have to teach after that per unit system, because we represent everything dimensionless quantity. For example, transformer you have studied. Say low voltage, for example, low voltage side is say, for example, 3 kV, high voltage side is 11 kV. But we represent in per unit system such that whether it is primary or secondary, in per unit you will find both irrespective of their voltage level. Later you will see that. Right. So in this case, that's why it is written in per unit, but not yet your taught, but it will come later. Of the individual maximum demand of the ith load, if Ci is the contribution factor of the ith load or to the group of maximum demand, then Pc will be, I mean, P1, P2, Pn, whatever it is, up to n number of consumers, whatever is there, your what you call that they demand that what is their contribution, 30%, 40% like this. So C1 into P1 plus C2 into P2 plus up to Cn into Pn. That is your is Pc, right? And therefore Pc will be is equal to I is equal to 1 to n Ci Pi, right? This is actually how much your coincident maximum coincident demand, right? And from equation 12 and 15, that means this equation, this 12 and 15, that this one, if you substitute, then Cf, the contribution factor will be I is equal to 1 to n Ci Pi upon sigma I is equal to 1 to n Pi. These are very simple, actually. These are nothing, actually, right?
So,
So this is called contribution factor. Now,
so like,
tell me.
so like, contribution factor and this.
I can hear you. What? Tell. Tell clearly. Can't hear you. Hello.
Can you hear me, sir? Hello.
Bring that mic. Now I can hear you. Yes.
Yeah. So previously also we discussed just above that 1 by ft, right? So what is the difference between that CF and this CF? That is.
Which one?
So like
Here also
1.13.
coincident factor. Hold on. This is called, hold on, this is your coincidence factor, that Cf is equal to Pc upon I is equal to 1 to n Pi, right? This is coincident factor, right? And then contribution factor is it is given in the per unit of individual thing. Then we are trying to relate this your what you call coincidence factor, and the is equal to your this is Pc is the contribution factor. Actually, what happened that I'll tell you that when you represent in per unit, this P1, P2, Pn, it will be all dimensionless quantity, and you will find it will be whatever, how much, for example, suppose P1 is 0.8, P2 is 0.3, Pn is up to say two cases, right? And C1 is say 30% of it is going, and your C2 is say 40%. So you add all this, right? And that is your call Pc. So Pc can be written as I is equal to 1 to n Ci Pi. Therefore, this coincident factor, we are relating this coincident factor Cf, that Pc we are substituting. This is your what you call that I is equal to 1 to n Ci Pi divided by I is equal to 1 to n Pi. So coincident factor actually your coincident maximum demand by sum of individual maximum demand. Right. The idea is that this P1, P2, Pn is the maximum demand of individual maximum demand, right? But when we are trying to coincident maximum demand at a particular hour, you see how much contributed by this P1, by the size it is industrial consumer, how much percentage is this one of the maximum one, this P1, P2 individual maximum demand, P1, P2 up to Pn, but it is not happening at all the time, right? That's why this C1, C2, that percentage term has come. That's why PC coincident load or this thing, coincident maximum demand, I is equal to 1 to n CI/PI. So this is actually your coincident factor, CF, we are trying to relate with this one, right? So CF is equal to I is equal to 1 to n CI/PI upon I is equal to 1 to n PI, right? So this will,
Sir,
tell me.
so like how is the contribution factor found out? Because like as you
The
said, if you,
contribution factor is it is basically, let me tell you, this is coincident factor. Contribution factor is only this much, PC, right? How much percentage is contributing, right? Nothing else, nothing else. And this is your total PC, right? Nothing else. And I am trying to relate this your what you call this coincident factor with this contribution term. Nothing else, nothing else. Some special cases are there in that. Nothing else. There is actually, it is in per unit, it is a dimensionless quantity. In per unit, later we will see that after third or fourth chapter, I think fifth chapter or fourth chapter, that per unit system, it will take 2 hours or 3 hours to teach, right? So this is actually dimensionless quantity, and this is actually contributing. That is how much it is contributing. That CI is the contribution factor of the ith load. That means as a whole, if you take that, actually, just hold on. For example, just hold on. Let me go to this. For example, I draw many things, right? So this is individual maximum demand. This is another individual maximum demand. This is another individual maximum demand. But when you come here at the peak here, this no peak is happening here, right? So whatever its peak, it may be less than that. Some fraction is there, C1. Here also some fraction will be there, C2. Here also there some fraction will be there for C3, this one, right? So it is not matching with this thing, right? So this is maximum demand. This is maximum, this is individual maximum demand, right? When you are going to PC, so it is not individual, you are not summing it up, right? What you are doing is how much percentage of this, how much percentage of this, how much. So C1, C2, C3, that is whatever it is, this is actually called the contribution factor. I'll give you example from graphical thing. From there you can find out that what is the percentage of it. And that is actually C1, C2 contribution factor. And as a whole, this is the total contribution, or what you call that total coincident demand. Got it or not?
yes, sir, yes.
This is a simple thing, and therefore coincident factor will be, if you substitute in equation this one, or what you call in this equation, PC is equal to, then you will get this equation. A simple thing. Now some cases, that case 1, if P1, P2 is equal to P3, or if all are P, if all are is equal to P, in this case, if P1, P2, P3, all are is equal to P, right? Then this equation will become simply P into sigma Ci divided by N into P, because P term will be added N times. So that's why it is your P into N, and this is P into sigma Ci. So contribution factor will be I is equal to, coincident factor will be I is equal to 1 to N Ci upon N, right? Because N times you are adding that sigma term, right? If all are equal, right? So that's why it is this is your coincident factor. In the case 2, if C1, C2 all are same, right? If all are same, then you, in this equation, if C1, C2 all are same, so C should be common, and sigma Pi upon sigma Pi will be cancelled. Summation, of course, I is equal to 1 to N. So in that case, coincident factor will be C, right? So this is your what you call some terminology, but they use particular in the generating plant. Most of the cases it is generating plant, right? So next is load factor. So load factor basically average load by maximum load or peak load, right? For for a given duration of time, it may be for 24 hours, it may be for 1 month, it may be for annual also, right? So every hour average load means because nowadays, because supercomputer or fasting computing things are available. So for example, later graphically with example I'll tell you. Suppose 24 hours average load you want to find, say hourly basis you calculate. So at every hour you find out what is the load in kilowatts, say, right? So every hour, all 24 hours load you add, and out of these 24 hours you see what is the peak load. So load factor will be average load by peak load. So all 24 hours load you add divided by 24, that will be your average load, right? And then the peak load, that out of 24 hours you see which is the peak, where is the peak, what is the peak load divided by peak load. So load factor will be average load by peak load. It is something like this. Later I'll tell you, it is something like this. For example, For example, you take suppose some 24 hours, right? There's this 0 hours, say midnight, right? So 24 hours, just midnight to midnight, or 6 a.m. to next morning 6 a.m., right? 6 a.m. to 6 a.m. So every hour, because every minute you cannot do because computation will be high. Generally, they do half an hour and an hour basis. So every hour you see what is the load, right? Every hour you see what is the load. This way, every hour you add. Right, so all the load, all the 24 hours load you add. Suppose Pi you get, I is equal to 1 to 24. This all the load you add divided by 24. This will be your average load, right? And every hour, as you are doing it, suppose for this one you are doing it, or combine, any one you take, and this is your peak load, whatever it is, for the combined one. So and every hour you are making this load, make how much it is, and whatever is the peak, this is the peak. So whatever you get, this is average load divided by this peak one. That will give you the average load factor. Load factor. So load factor is equal to average load. And if you want to make it in the terms of energy, then multiply numerator and denominator by T. Time may be 24 hours, maybe in 1 month, maybe annual, doesn't matter. So in terms of energy, if you want to make, then you multiply by T into T, right? That is energy served, and this is peak load into T. So that is your definition of load factor, right? Annual load factor is total annual energy produced divided by annual peak load into 8,760 hours. Generally, just let me tell you one thing. Generally, whenever, particularly for the research purpose, whenever we are doing it, we are taking annual load, right? 24 hours. For example, I'll tell you something about this, that whatever little bit research and this microgrid and distribution system I do, that is totally downstream, 11 kV voltage or below that, right? So if you see in our institute, that solar PV panel is there. So there, that data for 24 hour, for your hourly basis or half an hour basis, that solar power generation, for example, directly it is available. Actually, I use the data, right? It is available, right? So you will be knowing, for example, suppose if you want to find out what is the annual load factor of the solar power generation, only daytime, it actually your what you call your what you call it generates power, right? So whatever you have, and on the rooftop in our library, from that data you use, right? Only pattern you use, not data, pattern, how the solar power generation pattern. That pattern and other things, if I find time at the end of this course, I'll tell you something on microgrid and other thing. So question is that, suppose daytime only it generates power, nighttime no power, right? So whatever energy is produced, that you can make it, and you know what will be the annual peak power load of this solar power generation, multiply by 8760. That will give you annual load factor of the solar power generation. Similarly, in power plant, there are so many units, right? Say thermal power plant, so many units, right? And in that case, what will happen, that they have the meter, they have the energy meter. So how much energy is served or energy is produced annually, that they know, and also they know what is the annual peak load, right? Multiply by 8760, that will give you annual load factor, and that they use it. If load factor is high, means that is the better use of plant. If load factor is poor, means that is not the good, better use of plant. Maybe some of the units are shut down, maybe there are some faults, right? So many issues are there. So anyway, if load factor is above 0.6 or so, that means it's a very good use of the generating plant, right? Another thing is the loss factor. So in the network, power loss is the just hold on, if somebody wants to join or not, let me see, just hold on. No. So that is your, whenever your what you call that power loss, it is basically, that is square of the current, right? Power loss is proportional to the square of the current, hence the square of the load, right? Suppose, for example, if I say it is I square R, I'm just putting it, suppose load is P in terms of rather than power, suppose current, suppose P, the loss is also square of the, proportional to the square of the power, because it's just a rough calculation, VI cos phi is equal to power, right? If you assume V is constant, power factor is constant, then I is equal to P upon V cos phi. If it is I square, if it is proportional to I square, means it is proportional to P square, right? So loss factor, instead of LF, we are using load factor. That's why I use LLF, double LF, right? It is average power loss by peak loss. That means, I'll tell you, later you will know much more. For example, every hour you have the load, right? So every hour you have the load means, that means later you will know how this power system operates, right? So in power system is a big network. So by running power flow program, we can get the loss at every hour, right? If you know the loss at every hour, divided by suppose 24 hours. So if 24 hours loss you add, divided by 24, same as your average load, the way we have found out load factor, loss factor also. And then at a peak load, the loss will be maximum. So run the power flow program and see what is the loss, divide by the peak loss. So loss factor will be is equal to your average power loss divided by power loss at peak load. And if you multiply by T and T, then you will get annual your average energy loss, right, divided by power loss into the time. This is the loss factor. So this is actually what you call, we define as a loss factor. And these are the, particularly when you come to the downstream, actually generating plant is generating power, right? After that, your what you call power is being transmitted, then coming to the downstream. Apart from industrial consumers, commercial, agriculture and residential, we get the power, right? Ultimately, and there will be power loss. When power is distributed to the transmission line, there will be power loss. I square R loss will be there. Later we will see that how things how they operate, right? And you have some ideas that long tower is going, transmission lines are there, how transmission lines are made. Something we'll discuss, but not the design part in any way. So this is your what you call that your loss factor, right? So just take this example, right? Just take this small example. Suppose this power station supplies the load as stipulated below. Suppose 6 a.m. to 8 a.m. the load is 1.2 megawatt. It is given. 8 a.m. to 9 a.m. 2 megawatt. 9 a.m. to 12 noon 3 megawatt. This way 6 a.m. to 6 a.m. next day 6 a.m. that is 5 a.m. to 6 a.m. it is 0.8 megawatt. This way it is given. The data is given. 24 hours data is given. Right. So plot the load curve and find out the load factor. Determine the proper number and size of generating units to supply this load. This is from your intuition, you'll make it. In reality, they run optimization program and lot of issues are there. Right. It is not just a thumb rule, you will do it. A lot of things are there. Later, I'll tell you when I'll teach load frequency control, their control part is there. Some controller, integral controller, proportional controller, derivative controller. Actually, reality how industry they operate, little bit I'll tell you when I'll teach the load frequency control, right? Then find the reserve capacity of the plant and the plant factor. Find out the operating schedule of the generating unit selected. These are from intuition, you have to make it. Because otherwise, for higher studies, master degree and research studies, things are different. But from the classroom point of view, this is this example will your what you call help you to understand. First, you have to plot the load curve. So data are given 6 to 8 a.m. 1.2 megawatt. You draw a staircase. Don't draw continuous plot. You draw a staircase. So 6 to 8, it is your what you call, it is given 1.2 megawatt. So 6 to 8, 1.2 megawatt. Then your 8 to 9, right? 8 to 9, you jump from 8 to 9, it is 2 megawatt. Then 9 to 12, right? So then your so 8 to 9, your 2 megawatt. Then your 9 to 12 noon, it is 3 megawatt. That is the peak, out of which you see 3 megawatt is the peak. This is the peak, right? And then your 12 noon to 2 p.m. 1.5 your what you call 12. From here it will jump again, and from 12 to your 2 p.m. it is your 1.5 megawatt. This way you plot this staircase graph and you come up to this. This is your load curve plotting, right? So this side is megawatt, and this is 6 a.m. to 6 a.m. that is 24 hours, right? And therefore unit generated during 24 hours, because it is, for example, how you do it, unit generated 6 to 8 a.m. 2 hours. So 1.2 into 2, 8 to 9, 1 hour, 2 into 1, 9 to 12, 3 hours, 3 into 3, then 12 to 2, 2 hours, 1.5 into 2, 2 to 6, 4 hours, 2.5 into 4, 6 to 8, 2 hours, 1.8 into 2, 8 to 9, 2 into 1, 9 to 11, 2 into 1, 11 to 11 p.m. to 5 a.m. it will be 6 hours. So 6 into 0.5, and then 5 to 6, 1 into 0.8. Same calculation has been made it here, right? Whatever I said, same thing has been. So that is your 37.8 megawatt hour, right? Just nothing, you take 2 hours, multiply by this, and then 8 to 9, 1 hour into 2, and so on, right? This same way it has been made here. So it is 37.8 megawatts. So average load will be unit generated by time in hours. So this is your unit generated, and time is 24 hours. So it will be 1.575 megawatt. So this is your average load. 1.5. If you draw a horizontal line parallel to your x-axis, that is time axis, so it will be 1.575. So it is 1 to 2. Somewhere it will be here. If you draw a line, it will be average load, right? That is 1.575. And then load factor will be average load by maximum load. So average load is 1.575 megawatt, and maximum load is 3 megawatt. This is the 3, because out of all this, you can see 3 megawatt is the maximum. So average load will be your load to your 1.575 divided by 3. So 0.525. This is the load factor, right? Then maximum demand is 3 megawatt. Therefore, just it is an intuition. Anybody can do anything. In reality, little, I think in your course it may not be there. Little bit will be there. A lot of issues are there, right? Generating characteristics has different fuel characteristic, cost characteristics. So many issues are there, right? If it is thermal mix-up of thermal power plant has different type of units: reheat type turbine, non-reheat type turbine. So many issues are there. The double reheater also will be there. Lot of issues are there. But anyway, so maximum is 3 megawatt, and you are therefore you can choose a 4 generating units of 1 megawatt. This is from your intuition, right? I have not made any research or anything, right? So that means if you choose maximum 3 megawatt unit, if 4 you are choosing, because if one is out, say not in operating, say another one you can start. If 2 are out, then you cannot supply the full load, because only 2 megawatts maximum will be available, right? So each may be selected. During the period of maximum demand of 3 units will operate, and one unit will remain as standby, that is reserve. So plant capacity will be 4 megawatt. This is from intuition. I didn't. You can do 5 also, no problem, right? Or 6 also, no problem, right? Plant capacity is 4 megawatt. So reserve capacity will be 4 minus 3, 1 megawatt. If you choose 5 unit of 1 megawatt each, it will be 5 megawatt. So reserve capacity will be 2 megawatt, right? Actually, in the past, rather than nowadays very large units, they are using 500 megawatts, 1000 megawatt generating units, and they are very reliable. And when you are suppose you have 100 megawatt, suppose you are installing 105 units of 100 megawatt each, and you are installing only single unit 500 megawatt each. Now it comes to the economics. If you install 500 megawatt unit, your investment will be less. But if you individually, if you make 400 megawatt each unit, your investment will be more, because cost will be more, because 5 different generating units you are installing. But for single unit of 500 megawatt, if there is any fault or anything, that whole 500 megawatt will be out. So reliability is less. But if you have 5 units of each one is 100 megawatt, if one unit is out of order, at least other 4 units can supply 400 megawatt. So reliability is more. So compromise has to be made. But nowadays, cost of everything is going on. Generally, they are preferring of installing higher generating unit, higher capacity generating unit, right? So earlier in the past also, they used to make rather than large unit, they used to make small rating unit, 4 or 5, right? So plant factor will be, so this is your reserve capacity, and plant factor will be actual energy produced by maximum plant rating into T. So actual energy produced, we have seen it is here, that 37.8 megawatt hour, right? And your 4 generating units are there, 4 megawatt, right? And 24 hours duration. So it is 4 into 24. It will be 0.39375. Right. If you make 5 generating unit, then it will be 5 into 24. I have used 4 only. If you make only 3, then it will be 3 into 24. Anyway, this is the plant factor. Then now operating schedule. This is no. I have just made it. You can make it of your own also. One generating. I mean, looking at this, looking at this load curve. You please make it of your own. I have made something here, right? I have made something here, that operating one generating unit 24 hours it will operate, right? And second generating unit 1 megawatt 6 a.m. to 9 p.m. 15 hours. Third generating unit 9 to 12 noon, and 2 to 6 7 hours, right? Looking at this load curve, you just make it such that at least this power is being supplied, right? It is, I have just made it of my own. You can make it in other way also, right? But in reality, they run unit commitment, another thing, how which will operate, what will be the minimum fuel costs. So many issues are there. But here, just your what you call, just you whatever you are this thing. The way, if I give you an exam, you make it of your own, right? And see that answers should be different from each one, right? Everybody cannot have photographic memory that everybody's answer will be same. It cannot be done, right? So so anyway, this is your what you call, this is your that operating schedule. This is up to you only. I have made in one way, you can make it in many other ways, right? Now next example. A generating station has a maximum demand of 80 megawatt and a connected load of 150 megawatt. Is maximum demand 80 megawatt and connected load 150 megawatt. If megawatt hour generated in a year, it is given, that is energy generated. Megawatt hour means energy, annual energy generated is 400 into 10 to the power 3, that is 4 lakh megawatt hour, right? So calculate the load factor, demand factor, these two. So maximum demand is given 80 megawatt and connected load is 150 megawatt. And unit generated in a year, that is annual unit generation, 400 into 10 to the power 3 megawatt hour. So total number of hours in a year is 8760. Therefore, average load will be this one, 400 into 10 to the power 3 divided by 8760. So 45.662 megawatt, right? Hope these calculations are correct, except one or two places. You just press the calculator, right? And load factor will be average load by maximum load. So average load is this much, and maximum is given here 80 megawatt, right? Therefore, 45.662 upon 80, so 0.57. So this will be your load factor, right? And then demand factor is actually maximum demand by connected load. So here it is maximum demand is 80 and connected load is 150. So directly you can find out that 80 upon 150. So 0.533, right? This is demand factor. Next, this example. Everything I'm explaining such that later you will not face any problem. A sample distribution system is shown in figure. This is sub-transmission system. This is step down transformer, right? So one of the feeder, two feeders are there. One is supplying industrial load, and feeder means it is a distribution line which is feeding power to the different load. That is feeder, right? So this is actually industrial load, and this is two feeders are there. This is supplying residential load, and some other feeder reserved for future load. Something is like this, and this is a transformer, and this is and this is your distribution substation. For example, this side may be 33 kV, this side may be 11 kV, this side may be 66, this side 11, this side may be 66. This side cannot be 33 because this is a residential load. Though this side may be your, I can say this is 11 kV, and this side your what you call 400 volt or 430 volt, and this industrial load means small industries, right? So one of the feeders supplies on industrial load with a peak of 2 megawatt, and the other supplies residential load with a peak of 2 megawatt. So this industrial load is peak 2, residential also peak 2, but combined peak load is 3 megawatt because two peaks will never happen together, right? It's a peak will occur at different time, right? So you have to find out the diversity factor of the load connected to the transformer. That means these are the load, industrial load and residential load. The load diversity of the load connected to transformer, the coincidence factor of the load connected to the transformer, right? These are the things. So from equation 1.7, diversity factor is that FD is equal to sigma I is equal to 1 to n pi upon PC. Here only two consumers are there, industrial and residential, so n is equal to 2. Right. So I is equal to 1 to n is equal to 2 pi divided by PC. So P1 plus P2 upon PC. So coincident combined peak demand is 3 megawatt. That means PC is 3 megawatt and P1 is 2 megawatt, P2 also 2 megawatt because each one peak is 2 megawatt. Right. Industrial is 2 megawatt here and residential also 2 megawatt. Therefore, it is your diversity factor 2 plus 2 upon 3. So 1.33. Now load diversity, it is sum of individual maximum demand, that is I is equal to 1 to n pi minus that your PC, right? So n is equal to 2, so it is 2 plus 2 4 minus PC is equal to 3, so it is 1 megawatt, right? That is the load diversity. That is sum of individual maximum demand minus that combined maximum demand, right? So it is actually your 1 megawatt. And from equation 1.13, coincidence factor is your 1 upon your diversity factor, that is 0.75. It is reciprocal of that. We have got 1.33, so it is reciprocal of 1 upon FD diversity factor. So that is your 0.75, right? So now this one, this is your relationship between load factor and loss factor, right? So this is very, this is very rough estimation. In reality, it is slightly different. And on 3 cases are here. Just you see this very simple equation, right? And initially I told you that power loss is proportional to the square of the current. Generally, VI cos phi is equal to power. If we assume power factor is constant, voltage is constant, then I is equal to P upon V cos phi in general, right? So if V is constant, cos phi is constant, if power loss is proportional to the square of the current, that means it is proportional to the square of the power. That concept we'll use it here, right? So I mean, it is something like this. Suppose generally we use VI cos phi is equal to power, generally, right? So I is equal to P upon V cos phi. If V is constant, assuming that cos phi is also constant, therefore I is equal to actually I is equal to K into P, right? Therefore, the power loss is proportional to the I square, that is magnitude of the current. If it is so, then power loss is proportional to P square also, right? This concept we'll use here. So suppose this is very rough relationship we are going to use it, right? So how to relate the load factor and the loss factor? Suppose this P for a peak load, say peak load P2, this is the peak load P2. This is occurring for time 0 to t. Total time duration is capital T, but peak load, that is the P2, is occurring up to time from 0 to t. Say time duration is, and off-peak load is P1, and that is occurring from time small t to capital T. That is duration is capital T minus small t. Right. This duration from here to here, it is capital T minus small t. Similarly, during peak load, this will be peak power loss. So power loss is maximum power loss is L2. It is from 0 to time t. And off-peak power load, that is your this one is your from small t to capital T. That is the duration is capital T minus small t. Right. And if you see the average load, this is your average load, right? If you add average load, means you have to see that your P2 plus you have to add P1 and total time duration is T, right? In any way. So this is similarly what called average loss, right? A gas line is drawn. This is the average load and this is the average loss, right? Now, assume that the peak load T2 and peak loss is L2 and that off-peak load T1 and loss is L1. Therefore, load factor will be average upon P max, right? So P average is average load. So P average upon P2 because P2 is the maximum, right? Now P average will be generally what will happen in terms of energy. And P average will be P2 into this small t, right? P2 into t, this small t plus this P1 is because the duration is t, and this P1, this one will be your P1 into capital T minus small t, capital T minus by the total duration is t. Therefore, your P average will be 2 into small t plus P1 into t minus. Hold on, somebody is joining. I'm not sure. Yes. Rohit is out. Yes, Rohit, maybe you are sleeping. Anyway, doesn't. As I related you in the class also. After teaching for some time, one or two things I can do. For example, one day I was taking classes. Maybe it was modern science classes. Maybe I cannot recall but total number of students in 30 class many years back. So when I started taking class, one boy came in around 5 minutes. He sat in a very fast row in the corner. Then when I took class, I found he slept. When class was over, I found still he is sleeping. Then I went to him and put my hand on the back of that boy. Right. And boy looked at me. I said, class is over. So he started smiling. So I do not disturb anyone. And this I have learned from my when I was young, I have learned from my senior teachers
different thing. So I didn't tell. I said, then I asked why you were late. He said, sir, last night I was studying actually. If you are studying, it is fine. But if you are not studying, was with your friends, something is different. Right? Anyway. So Rohit, anyway, try to join. It doesn't matter. So then the P average will be 2 into 20, then this is the P average that you got, right? That is your load factor. So if you substitute the P average, then you will be something like this. The load factor will be 2 into T plus T1 into T minus, that is capital T by 2 into T. Now, if you each term you divide by 2 into T, so load factor will be T upon T because T2 will cancel, and here also it will be P1 upon T in capital T minus T upon capital T. Right. Similarly, loss factor also will follow the same way. L average upon L max, that is L average upon L2. Right. Because L is the loss happening at hours. Right. L max, the max loss is equal to L2. L average loss. Right. Therefore, L average will be L2 small, same as before. Earlier it was 2 into for the load plus 1 into capital T minus small T upon T. Right. So if you find out the loss factor, then same thing it is L2 into plus L1 into minus capital T minus small T upon L2 into T. This is the typical error. This is the typical error. Correct. T is the load duration. That is your this small T. This is the load duration. This small T. Right. So therefore this one. Now what can go is and capital T minus small T the upload duration. Like I told you. Right. I told you that all loss will happen. All loss, all loss will start in transformer. Right. So L1, that the loss of upload and load can be expressed as the upload L1 may be K into L1 square and L2 is equal to K into P2 square. I just told you that if it is proportional to the current, magnitude of the current is square of the load. Right. So L1 L2 is this much. If you substitute L1 is equal to K into L1 square and L2 is equal to K into P2 square in expression 1.8. Right. Then if you simplify, it will get loss factor will be T upon T plus P1 upon P2 whole square into T my capital T minus T upon capital T. Right. Now some cases we have to right. So load factor is coming like this. Right. Loss factor is coming like this. Right. Based on certain assumption. Now case of peak load. When peak load is 0, that means P1 is 0 and L1 is 0. Right. Here in this equation, P1 is 0. Right. Then load factor will be small T upon capital T. Right. P1 is 0. Right. Because no optic. And similarly, here also if P1 is 0, loss factor will be also small T upon capital T. Therefore, load factor is equal to loss factor will be T upon T and there is no optic load, right? That is the load factor is equal to loss factor and equal to small T upon capital T. So because some relationship we have to establish, right? Similarly, if T tends to 0, right? In this case, T tends to 0 means that is your peak is very duration is very less and everything is optic in this thing. In that case, it tends to 0. Capital T minus T upon capital T tends to 1. Because if it tends to 0, it will tends to 1. Therefore, from this expression you can derive, just you can see this one and this one, right? These two, if T minus T upon T is less than 1 and T tends to 0, therefore, you will find that in this equation you will find that T tends to 0, this term may not be there. Minus P upon H tends to 1, it will be P1 upon P2. Right. Here, and in this equation, T tends to 0, and capital T minus T upon T tends to 1, P1 upon P2 square. Right. Therefore, your loss factor tends to load factor square. Right. Because load factor will be 1 upon P2, and loss factor will be 1 upon P2 square, it will be changed to LF square. Right. And third one, this is a small exercise to you. When T tends to capital E, it will be loss factor will be tend to load factor. This is a small exercise to you. Right. So this is you find out how you will do this. So when T tends to T, then loss factor will be equal to load factor. So if because of this from this relationship, one is loss factor is equal to load factor for this condition. Another is extreme case, load factor tends to load factor square. And another case when T tends to capital T, right? Small t tends to capital T. Load is steady, right? In that case, loss factor tends to load factor. From this, you can find out the loss factor will be less than load factor and greater than equal to load factor square. This is true actually. This is true. Generally, from statistical data, when data collected from the distribution network and statistical data after the analysis, it has been found in that town or city areas, this is true. 0.3 into LF into plus 0.7 into LF square. But when you come to the rural side, it will be actually 0.8 LF and 0.8 LF square and 0.2 LF. This is true for the town or city areas, and for rural areas, whatever statistical data, this is actually 0.8 into LF square plus 0.2 into LF. Right. Some more or less it varies like this. So loss factor or load factor can be related to this. So if you know the load factor, so roughly you will get some idea about the loss factor. Right. Up to this is okay or not? Up to this is okay or not?
Yes, sir.
Little bit practice, because I will because it is only online exam. And 105 students have registered so far. Yesterday I have seen it. When I send this thing, and when I take the exam, it will be made in several groups, right? And you practice little bit, because later you will see mathematics. Each exam will be conducted on Wednesday only, Wednesday morning, because 2 hours time is there. But exam will be for 1 hour, 21 hour, 30 minutes, right? And I give 3, for example, I give sufficient 3 or 4 problems, and sufficient time will be there, and such that you can do it. But you have to do a lot of calculations. Later you will see that. And calculator should be properly used. If any calculation is missed, everything will be wrong. But if your methodology is correct, if everything is correct, by mistake you have taken the wrong data, by mistake if you have taken your what you call wrong calculation, at least I give 80% marks out of it. I mean, if 10 marks is given, I give 8 marks. If I see everything is correct, by mistake calculation is wrong, at the end of that answer is wrong, but everything is correct, I give 80 to 90% mark. That I consider. I do not go for digital marking, that 1 or 0 or 0 or 1. I will see everything, right? Anyway, load growth. Actually, load growth will be there, because so many industries are coming, right? And new residence houses are coming. So load growth will be there. It depends from the city to city, town to town, right? So whenever you have the load growth, that your PM will be equal to some load, right? 1 plus g to the power m. M is the year, number of year, and g is the load growth. Generally, it happens. Generally, it varies from rural area to city area, maybe 3 to 7%, right? Every year. So that's this is the, suppose this is the load at 0th year. I mean, at this very moment, right? And suppose next year, if it is 3%, it will be g is 0.03. And next year it will be 1, it will be 1.03 multiplied by P0. If it is next to next year, if m is equal to 2, and if g is continued to be 3%, 1.03 square. This way we consider the load growth, right? If the load increases, loss also increases, but that is beyond the scope. But this is how things are. Multi-phase system we will not discuss. It is there, better you skip it, right? Better you skip it. No need to study. And one more example is there, similar to that only. Please do yourself, please do yourself this example. And now disadvantage of low power factor. This one, of course, you will do of your own. Everything is solved. Multi-phase system, no need, right? And now disadvantages of low power factor. Generally, for 3-phase system, you know, √3 VI cos phi is equal to this thing. This is actually, if load is PL and terminal voltage is V, and there is 3-phase system, so IL is equal to PL upon √3 V cos phi. So if PL and V are constant, the load current IL is inversely proportional to the power factor, that is cos phi, right? That means if load is constant, right, and V is constant, right? So if these two are constant, then IL is inversely proportional to the your power factor, right? If IL is large, that means if power factor is poor, then IL will be large.
the poor power factor is the system has the following disadvantages. Rating of generators and transformers are inversely proportional to the power factor. Thus, generators and transformers are required to deliver same load at low power factor. Hence, system KV or MVA supply will increase. A poor power factor means that it will consume more reactive power from the your source, right? Suppose you are using a device, its power factor is 0.7, for example, right? That means, suppose it is a 500 drawing 500 kilowatt, means at the same time it is drawing 500 kilowatt because power factor is 0.707, right? That means if it draws more reactive power from the line, that means in general the current will increase, because current is equal to, in general, ID plus JIQ, direct axis component as well as quadrature axis component. So IQ will increase. In general, current magnitude will be ID square plus IQ square. It is something like this. It is something like this. Suppose, just hold on. Suppose it is, suppose current is generally, say AC current, I is equal to ID plus GIQ, right? So if your this thing, what you call reactive power is more, then this IQ component will be more. So when you take the magnitude of I, right? So earlier I think I wrote something. I am not masterpiece of all these things. This online thing. Oh, this is coming. Something I have pressed. Just hold on. That's why here it will be there, right? So generally magnitude of I will be root over. Here also something I wrote. Let me go down. Here, let me make it. So I is equal to root over ID square plus IQ square, right? So question is that if your reactive power is more, this component will be more, this current will be more, right? Therefore, power loss will be more, because power loss, P loss is equal to, I'm putting magnitude only, into I square R, right? So that's why that your, if reactive power is more, that means power loss will be more. At the same time, as the current is flowing through the line is increasing, that means voltage drop in that line will be higher. That means the receiving end voltage will be poorer, right? So these are the bad effect of the operating any device at low power factor. At low power factor, transmission line, feeders or cable will have to carry more current. I told you, right? So more current means more power loss, and there will be voltage drop. So receiving end voltage may not be better. So power loss is proportional to the square of the current and inversely proportional to the square of the power factor. More power losses, I told you, right? And low lagging power factor is until large voltage drop. Same thing I told you, same thing written 3-4 times, but these are the concept. Low power factor means low voltage at the receiving end, power loss will increase, right, in the network. That's why every electrical devices must operate at higher power factor. Otherwise, what will happen? You have to supply those reactive power. That's why you will find, if you go to substation, there you will find that shunt capacitors are connected, right? It is connected. Later I'll tell you. Or you will find fax devices are connected. Fax devices are expensive, but fax devices are connected to compensate that those reactive load, right? Because synchronous generator and power plant, they are not sufficient capacity to supply those reactive power. Generally, it operates around 0.85 power factor, right? So you know how much reactive power it will supply. So that's why to compensate that those reactive load, that every substation you will find that shunt capacitors are connected. And various causes of low power factor. Most of the induction motor operates at lagging power factor. The power factor of this motor falls with the decrease of the load, right? Occurrence of increased supply main voltage during low voltage period. The magnetizing current of inductive reactances increase and power factor of the electrical plant as a whole comes down. Very low lagging power factor or agricultural motor pump set. It operates at very low power factor. Sometimes they operate for single phasing. I do not know, in machine you might have studied that your 3-phase induction machine, when one phase is out, how they operate that agricultural motor pump set. Arc lamp, electrical discharge lamp, some other electric equipments, and nowadays of course the computers and other things, they operate at low power factor, right? Arc furnace and induction furnaces also operate at very low power factor, right? The average power factor sum of the electric are given in this thing, right? That is given on the top. So this is another example that we will study, very simple example, right? This we will study, everything is solved, right? All cannot be done, then it will take more time, right? And as an exercise, first one you will do it, you please write down 1.1. No, I will tell you when you will submit, but you will keep ready. 1.8, you need not use any graph sheet or anything, only plain white paper you will do it. This 1.1 you will do it, and 1.4, these two things you will do it. This for the first chapter as an assignment, 1.1 and 1.4. When you will submit the assignment, you need not write the whole problems. You will just put the solution, because I have the problem with me. You will put the solution, you will keep it ready. When I will ask you to submit, I'll give you just 7 or 6 or 7 days before that, I'll give you the date, this time you submit. So keep it ready such that you can submit immediately. So 1.1 and 1.4, only these two from your first chapter, right? Only these two will do, 1.1 and 1.4. And I'll tell you the time later, not now, but you keep it ready, right? Generally I'll collect just 15 days. So what is the official time of this closing the semester? Maybe first week of April. I have to check it, right? I'll let you know. But all these things I'll collect perhaps in the middle of March or so. Whatever will be done, because many assignments will be given. Some special assignment will be given. There you have to later, right? But only 2 problems out of 5, 1.1 and 1.4, right? Next is resistance and inductance of transmission line, right? So the resistance, resistance already have studied from your higher secondary physics, right? So only thing is that you due to this pandemic situation, you didn't see the lab, right? And could not do the experiment laboratory. But anyway, this present pandemic situation has compelled us to do so virtually everything, right? Anyway, so resistance and inductance of transmission line. This is very crucial for transmission line. So whenever power system engineering is that branch of electrical engineering which concerns itself with the technology of generation, transmission and distribution of electrical energy. So as the day by day, if you see that the power system actually, that it lines everything is a complexity has developed. Electric power system is I told you, the largest man-made dynamic system on the earth, and very complex system, right? Because everything operates at very high voltage level, right? So, and of course, although it is high voltage, but later I'll give you some thought that concept of virtual power plant is coming. So those are the latest concept, and some part of the world, based on that existing power system, this work has started. And in some part of the world, people are constructing new virtual power plant where no question of thermal generator, thermal, hydro or nuclear, nothing. It will be based on battery energy storage system and power electronic devices, and everything will be software based, right? So things are coming up slowly and slowly, and we call virtual power plant, right? Some differences are there between virtual power plant and microgrids. Later will be this thing, but things are going on. So things are changing. Electrical engineering, whatever we have now, it is changing very fast, right? So whenever you consider overhead transmission line, you have seen that tower has gone, and a transmission line consists of group of conductors running in parallel. Maybe in a phase, suppose A, B, C phase is there. On the top, neutral conductor is also there. If you watch any tower, you can see on the top neutral conductor is also there, right? So whenever if you see that sometimes 3 conductors are there, each conductor is in one phase, or sometimes group of conductors are there in one phase. For example, suppose 2 conductors may be there in one phase. That phase A, 2 conductors, 2 parallel conductors, phase B, 2 parallel conductors, phase C, 3 parallel conductors, 2 parallel conductors, each phase 2 parallel conductors each. So if you make 2 parallel conductors, then what will happen? Current division will be there. Naturally, power loss will be less along the line. Naturally, voltage drop will be less along the line, because 2 parallel conductor in each phase is equivalent impedance will be less up, right? And therefore, at the receiving end, that along the line voltage drop will be less. Therefore, at the receiving end, voltage will be better, right? 3 conductors may be there in each phase, right? Similarly, group of conductors, maybe 7, 8 conductors will be there in each phase, right? And while I was returning from before pandemic, of course, while I was returning from Roorkee IIT to Delhi airport, I have seen many places that many group of conductors are there in each phase, maybe 5, 6, or 6 conductors are there. I cannot recall, 6 conductors are there in each phase and transmission line is going, right? So that's such that it can transmit bulk of power. And each phase, it is not a single conductor. It may be 2 parallel conductor, maybe 3, maybe 4, maybe 5, maybe 6, right? Like this, such that your power transmitting capability will increase, power loss will be less, receiving end voltage will be better, right? So this group of conductors, right? So that means a transmission line generally has 4 parameters: resistance, inductance, capacitance, and shunt conductance, right? So shunt conductance account for leakage current flowing across insulators and ionized pathways in the air, right? So these are negligible. Conductance will, because every tower you will find insulators are there. That line is coming from insulator, it is going to another one, right? Because you have to bypass so many things such that there should not be, it should not touch the tower, right? So leakage current will be there due to accumulation of moisture on the your insulators, right? But those shunt conductance are negligible, right? And when transmission line is carrying alternating current, therefore you have to have magnetic field, therefore you have inductance, right? And certain things are beyond the scope of this course. That is when conductor is carrying AC current, that current density across your what you call its cross sectional area, it's when you're moving to the surface, right? The current density across in the cross sectional area, it is different at different point. Later we'll see that. But in that case, what happens that it internally it links the flux, and external also it links the flux, because it's carrying AC current. How we are assuming and what we are doing, that will do that. Another thing is that the current is carrying AC current, a conductor is carrying AC current, therefore charging capacitance also will be there. If you assume that conductor and ground as a 2 parallel path, so there will be line to ground, that capacitance will also form. That also need to be considered for high tension line, right? So, and resistance as usual will be there for any wire or any conductor will have resistance. So resistance also we have to consider, right? So first we will see that the resistance is very simple, but we will see the inductance, right? So line resistance, you know that rho L upon A. This you have studied from physics, right? So rho is the resistivity of conductor, L is the length of conductor, A cross sectional area of conductor. This is right? Rho L into A. So actually what happened? The conductor resistance is affected by 3 factors. One is frequency, another is spiraling, another is temperature. So the different detailed analysis are there, but we will not do that. Spiraling means conductor spirals. It is not a single conductor for the overhead transmission line. Later I will tell you. It may be one conductor will be centrally, it will be, that is steel conductor, and around that spiraling will be there for other conductors, right? So whatever length you see, that is not exact length. Exact length will be little more than that because of spiraling, right? And temperature, of course, with the increase of temperature, resistance will increase. One question I'll put later, right, regarding this temperature. So whatever DC resistance of a standard conductor is greater than the value given one, generally because of this thing, you're spiraling 1% for 3 and about 2% for concentrically standard conductors, right? So little bit more than whatever it is, but that is actually before spiraling also they know the length. Accordingly they see that what is the resistance, and generally they use aluminum conductor, right, and steel reinforced. Later we'll see that. And with the temperature, this you have studied. With temperature, that this is alpha 0 temperature coefficient of resistance at 0 degrees centigrade, and this that RT is equal to R0 1 plus alpha 0 T. This is for resistance, right? So at any 2 temperature, if you take T1 and T2, R2 upon R1 is equal to this one, right? For aluminum, 1 upon alpha 0 approximately 228. This is resistance. Resistance we need not bother. Now inductance. Resistance as simple, right? Inductance. So generally what happened, for our basic understanding of electromagnetic field theory, we know that a conductor carrying current has a magnetic field around it. Suppose Suppose you take a conductor. Suppose you take a conductor vertically, or put your pen vertically and wrap the by right hand. You wrap your conductor. Then if the thumb is the direction of the current, right hand, then your direction of the flux will be the other fingers, other four fingers. That is, it will be anti-clockwise, right? So this you know from your physics, right? So the magnetic lines of force are concentric circles, because conductor we are assuming it is cylindrical, having their centers at the center of the conductor and are arranged in planes perpendicular to the conductor. So generally voltage induced in a conductor, or that you know, that E is equal to d psi by dt volt, right? So where psi represent the flux linkages of the conductor in Weber turns, right? And it can be written as, if you go for a chain rule, you can written as d phi by di into di by dt, and it is A is equal to L into di by dt. Where L we define as d psi by d, the inductance in Henry's, right? This is from your high secondary physics also you have studied. In a linear magnetic circuit, because we are assuming linear, right? Saturation, forget about other thing, just you assume linear, right? Flux linkage vary linearly with the current, such that inductance remains constant and is given by. So that's why if we assume that a linear thing, that's why L is equal to d psi by di, right? And therefore it is given as L is equal to psi by I in Henry. Instead of d psi by di, you can assume L is equal to psi by I, right? So this is in Henry, or psi is equal to Li. This is also known to you as things, but if when we are talking now, we'll change some terminology. That if it is alternating current, say, then we make a flux linkage lambda. Lambda is equal to L, and I is the alternating current I, and lambda is the flux linkages. And current, instead of small I, we are just putting capital I. I is the AC current, and lambda is the flux linkage. Instead of psi, we are putting lambda is equal to Li, right? Now, if you use for Ampere's law, that is loop integral, that which relates magnetic field intensity H to the current I enclosed, then is a loop integral H into dl, it is equal to I enclosed. So this is actually Ampere's law, right? Therefore flux density, it is Weber per meter square or Tesla. Just one thing you tell no, this thing, that that day I asked first year student, nobody could answer. Perhaps you may answer, but don't search in the Google. That electrical engineering, all the units are name of the all great people like Farad, Henry, Hertz, Tesla, Weber, right? Also all the dielectric Ampere, voltage, right? Ohm, all the great people name, these all units are given. Edison also had a lot of contribution, but Edison name is nowhere in electric. What is the reason? What is the reason? Anybody? Anybody can tell me what is the reason? Look, Farad is there, Henry is there, right? Ampere is there, Volt is there, Ohm is there, Tesla is there, Weber is there, Hertz is there in frequency. Hertz died at very early age. I think 37 years he died, but he only showed the path of communication, whatever communication today, right? Any idea without searching in the Google? You know or not? You do not know or not? But Edison name is not there in any electrical engineering quantities unit. Any idea? Nobody?
Sir, apparently he stole the Tesla's idea about.
No.
Sir, mainly I think Edison worked with like DC like related things.
No. Anybody else? Actually, Edison actually that invented that electric chair for capital punishment, right? That is the reason his name is not included anywhere. You never knew it before, no? That's why you'll find. Although he had a lot of contribution, carbon filament lamp, fast power station, power supply system, everything from Edison started from 1882, right? But his name
Like
is not.
So like you mean that electric chair which is used for killing criminals, like
Those things, yes, per capital punishment, yes, that thing. They will find Edison name is not there anywhere. Right? Other people, they are all many other great people name you will find, right? So many things we will find, but his name will not find, right? Anyway, So anyway, so making use of Ampere's law, which relates magnetic field intensity H to the current I enclosed. So it is a loop integral. These things are very easy. Later you will find that integral H into dl is equal to I enclosed. Generally, flux density is B is equal to mu H, right? Mu is equal to mu 0 into mu R, Mu 0, 4 pi into 10 to the minus 7 Henry per meter. And mu R is the relative permeability of the, right? And this also you have studied in your higher secondary, right? So later, so one can obtain the flux linked with the circuit by integrating the flux density over any surface bounded by the conductors composing the circuit. Therefore, equation 2.6, this one, right, or what you call the inductance can be computed as replacing d by dt by j omega, right? And the steady state AC voltage drop due to alternating flux linkages can be computed as V is equal to j omega Li is equal to j omega lambda, right? Directly, what you call that it is given your E is equal to d psi by dt, and instead of psi is equal to lambda is equal to Li, di ddt we replace by j omega, right? And therefore, V is equal to j omega Li, that is j omega lambda, right? Similarly, the mutual inductance between two circuits is defined as the flux linkages of one circuit due to current in the second circuit. That means it is actually M21 is equal to lambda 21 upon I1 Henry. This is in the first year when you studied magnetic circuit. At that time, mutual inductance you have studied, right? Similarly, the voltage drop in the circuit 2 due to current in circuit 1, that is V j omega to MT1, right? M21. And I1 is equal to j omega lambda 21. So this is a magnetic circuit you have studied in the first year. That is your electrical technology course. So this is very simple thing that V is equal to only, you can remember this V is equal to j omega lambda, or M21 is equal to, although this may not be required later, right? This may not be required later. Now this is started just to show that inductance of a single conductor, right? For a single conductor. So how we will do this? After covering this today, I have to stop. Right. So transmission line actually are composed in parallel conductors, I told you, and can be assumed infinite long. If you assume that it is infinite long, therefore, what will happen? You consider is a loop of single turn, right? Then the return path is lying at infinity. This way it will give you a single turn. Right. First, we will develop expression for flux linkages of an isolated current carrying cylindrical conductor with return path lying at infinity. This will form a single turn circuit, right? We will assume it is single turn, which is an image, it is an assumption. And magnetic flux lines are concentric enclosed circles with direction given to the right hand rule. I told you right hand rule, you wrap the conductor, and finger is your thumb actually, the direction of the current, and the other fingers is the direction of the flux lines, right? So this you know, the right hand rule. To calculate the inductance of a conductor, it is necessary to consider the flux inside the conductor as well as the external to the conductor. Both we have to consider. So this we will see that how we will do that, right? So this division is helpful as the internal flux progressively links a smaller amount of current as we proceed inwards towards the center of the current, and the external flux always link the total current inside the conductor. That means inside the conductor also flux density is different at every point, and it is called skin effect. We will not study that, only little bit we will study. A detailed study available, Bessel function and other thing, but we will not do that, right? So division is helpful as the internal flux linkage progressively links a smaller current, so amount of current as we proceed inwards towards the center of the conductor. And that means from center to the conductor, when you are moving to the surface of the conductor, things that your what you call that internal flux is increasing, or in other way it is decreasing from surface to the center, right? And external flux, external flux means external to the conductor, it links the whole current of the conductor, right? So first we will see the internal one, right? Internal inductance. You will see it is independent of anything. For example, you consider this is a single cylindrical conductor. You assume the radius is r, small r. You assume a distance x from the center, and the thickness is dx, and arc distance you assume this is dl. This is arc, right? So question is that before saying anything, when I use cross section, area, everything, for example, you take a notebook. You suppose your notebook is 1 meter long and thickness is say dx, right? If you fold it, it will be like your hollow conductor. You fold it, and in that case, if you consider its thickness is dx and length is L, then cross-sectional area will be dx into 1 square meter, right? So that will come later. So for example, you take your notebook and fold it. Thickness is dx and length is L. You cut it. It will be rectangle. Area will be 1 into dx square meter, right? Therefore, this figure shows the cross section of a long cylindrical conductor of radius r carrying a sinusoidal current of RMS value I. The MMF, that is magnetomotive force, around a concentric closed circular path, radius x internal to the conductor, is inside the conductor. This is actually cross-sectional view of the conductor, right? As shown in figure 1, it is loop integral hx dl into ix. As it is a concentric, so this hx will be constant at every point. This magnetic field intensity ampere turns meter at a distance x meter from the center of the conductor. And ix is the current enclosed, that is current enclosed up to distance x, right? So since the field is symmetrical, because this is a cylindrical conductor, hx is constant at all the points, right? Therefore, it is a loop integral. So it will be 2 pi, dl will be your, this is arc distance. So circumference will be 2 pi x, right? Because up to x it is, into hx is equal to ix, right? Now we have to neglect the skin effect, right? If you neglect the skin effect, that means we assume that inside the conductor that your current density will remain same everywhere. That means suppose at a distance x, current is ix, is cross-sectional is ix square, and at the surface current is I, it is pi r square. So current density every point is same, right? That means your ix is equal to x square upon r square into I, right? So that's why here it is used that skin effect is neglected. As you uniform current density at every point of this cross section, the current density is uniform. That means ix is equal to, I just showed you that it will be ix upon pi x square is equal to I upon pi r square. That means ix actually is equal to pi x square upon pi r square into I, that is x square upon r square into I. This is ix, right? Now from equation 14, that is your, it is actually, it will be 2.14 and 2.15. Huh? This is a typographical error. It will be 2.14 and it will be 2.15. This is a correction. Huh? One of many places this thing is there. So it will be 2.14 and 2.15. So that means hx will be, from these two equations, hx will be ix upon 2 pi r square ampere turns per meter. Right. Now for a non-magnetic conductor with constant permeability mu 0, the magnetic flux density Bx at a distance x from the center, Bx will be mu 0 into Hx. So it will be mu 0 into, this is the Hx, Ix upon 2 pi square, r square, right? Mu 0 is the permeability of free space and is equal to, 4 pi into 10 to the minus 7 Henry per meter. Now the differential flux, that is d phi x here in the small thickness dx, the differential flux d phi x for a small region of thickness dx and 1 meter length of the conductor. I told you the you just fold your notebook. The thickness is dx and length is 1. You cut it. It is like a conductor. You just cut it. So length is 1 meter and thickness is dx. So area is dx into 1 square meter. So d phi x will be bx into dx into 1. That way it is written, right? So mu 0 into I for 1 meter length, right? That's why it is 1. Mu 0 into I upon 2 pi r square x into dx, right? Now, the thing is that here we have to use some fractional term. The flux d phi x links only the fraction of the conductor because it is a cross-sectional area, and although you are assuming current density will be uniform every point, at every point, but as you are moving toward the center, that flux linkages will be small. As you are moving towards the surface, it will increase. Therefore, we have to make it as a,
So can you repeat dx into 1 is the
you take your notebook, right? Thickness you assume dx, right? And length is 1 meter. Now you fold it, make a conductor. So it will be round shape like this. It will be, thickness will be dx, right? dl is the arc resistance, you forget it, right? The thickness will be dx. Now if you cut it, it will be a rectangle. So area will be what? dx into 1 square meter. Got it or not?
Yes, sir.
In the class, I take that notebook, right? Here I am not drawing it online, right? You take your notebook, the thickness is dx, you assume, and length is 1 meter. So that portion area will be dx into 1 square meter. That's why it is written, it is for 1 meter length, dx into r, because everything we're trying to find out your per meter, right? Now, the flux d phi x links only the fraction of the conductor. Therefore, on the assumption of uniform current density, only the fractional turn will take. It is in terms of cross-sectional area of this thing. Pi x square upon pi r square of the total current is linked by the flux. That means flux linkage d phi x will be this call. It is in your what you call cross-sectional area, right? Because current your what you call, as we are moving towards the center, the flux linkages will be decreasing, and as you are moving towards surface, it will link your what you call more current, right? Although we are assumed the current density is uniform across the your cross section of the conductor, right? Therefore, flux linkage d phi x will be x square upon r square into your d phi x. So this is the fractional turn we call inside the conductor, right? And this is that, and that means if you substitute this d phi x, it will be mu 0 into I upon 2 pi r to the power 4 x cube dx, right? Now, if you integrate from 0 to r, if you integrate this one, that will lambda internal flux linkage, lambda will be mu 0 I upon 8 pi Weber turns per meter, right? Therefore, lambda internal upon I, whatever you will get, that is your I am putting mu 0 first, then L internal will be lambda internal upon I is equal to half into 10 to the power minus 7 Henry per meter. So it is actually this value actually independent of the radius of the conductor. Whether it is a very small cross-sectional conductor or very large conductor, this internal inductance is constant for all the conductor, right? This is true. Up to this is okay or not? Up to this is okay or not?
Sir, can you explain that fractional turn part?
Fractional turn actually, that is actually inside the conductor, that your what you call that current density you have assumed uniform, right? That is your Ix upon I is equal to x square upon r square. But inside the conductor, as you are approaching towards the surface to the center of the conductor, flux linkage is decreasing, right? But we have no physical turn here, no physical turn, right? Therefore, the flux link, that fractional turn, it is an assumption, we represent it by x square upon r square, right? That is we call that much thing will be your linked with that internal flux, assuming that flux density is uniform. This way we actually represent this fractional your turn, x square upon r square, right? This is actually based on the assumption of that skin effect is neglected. Later I'll tell you little bit of skin effect. Detailed explanation are there using Bessel function, that is highly mathematical, right? But this is actually, we assume that these are the fractional turn, because every point current density is uniform, but internal to the conductor flux linkages will be there, right? Suppose from diagram, suppose this is the flux line. For example, this is the flux line. Inside that, whatever current it will link, if you move towards the surface, it will link the more current. But if you come from the surface to this, it will link the more current. So how to relate the fractional turn? That is based on the current density. And that's why you have taken this x square upon r square. This is the philosophy. Right. Got it or not? Got it or not?
Okay, sir. Yes, sir.
Another point is, there is a question to you. Next class I'll ask you, find out. Although you have studied in higher secondary physics, so many things you have prepared for joint entrance exam, everything. Does temperature has any effect on inductance or not for any circuit? This is a question to you. Right. Whether temperature, like resistance we know has effect, a capacitance has any effect on temperature or not? Capacitance, you have studied in higher secondary physics. In your first year also physics, you have studied so many inductance, capacitance, so many circuit you might have done it. Capacitance has any effect on temperature or not? Resistance, you know, it has effect. Inductance and capacitance. Any idea? No idea, no? Inductance will find out whether there is any effect or not, temperature, because inductance is computed based on the magnetic field. right? Then you have to think whether temperature has any effects on magnetic field or not. That you think, right? So this is actually this internal inductance. It will remain constant irrespective of the radius of the conductor. Half into 10 to the power minus 7 Henry per meter, right? So I will not teach beyond this, because I know that in the classroom, whatever I have covered in classroom, it will take more than 2 hours. I know that. And here, because I am not writing anything on the blackboard, there on the blackboard I used to write many things apart from these notes and other thing. So I know this, and I'll give you an exercise. If you can, not tomorrow, you need not. So tomorrow you have a class. Next class, this will be covered, but one exercise is there. Hold on. One exercise is there based on inductor. This will be covered. Just one exercise is there. That, just hold on. Right from the beginning, instead of saying tomorrow, hold on. Just hold on. No, it is. Oh no, it is actually solved. Actually, I think I have solved in this case. I think very fast example. Just hold on. 2.1 maybe. 2.1. Where it has gone. Anyway. Hold on. See, if it is solved here, it may be solved, but I am telling you, suppose this internal inductance, just see that it is solved somewhere. It is this internal, I have solved it, I think. Suppose a hollow conductor you have taken. His inner radius is R1 and outer radius is R2. It is a hollow conductor, right? And you have to find out the internal inductance of that conductor. I think I have solved it. Somewhere it is there. For a hollow conductor, what will be the internal inductance? At that time, it is not independent of R1 or R2 for a hollow conductor, right? So anyway, thank you very much. Regarding those assignments, you need not submit right now, but you will make a plain paper. Don't use rule 1. White paper. Every page you will write your name and roll number, and each student will submit everything together, not separately. Today I have given 2. This way number will increase, and most probably all these things I'll ask you to submit perhaps in the middle of March and directly to me, right? So I'll give you a separate email address, not to this email address, through which I'm sending you the Google Meet link, right? And at that time. So thank you very much. Again, tomorrow we'll meet from 10 o'clock. Thank you very much. So I'm stopping sharing, right? So stop presenting this thing. Okay then. Thank you very much. Okay. Again, tomorrow we'll meet.
Thank you, sir.
Okay.